So, this is last but one chapter of the course on electric vehicles and renewable energy. This is a fairly large chapter, introduction of solar and wind energy, especially in India. I give you overview of what the deployments etc. are. Here I will go a little bit more into fundamentals of solar and wind energy. This will be the last chapter that I will teach. There are going to be two other lectures, one by Dr. Kaushal, who will talk about grid storage. Storage he has already done a bit, he will do a little more. And the second will be a guest lecture by Karthik, earlier from Ashok Leyland. Now he is a professor of practice at IIT Madras. So, let me straight away get into solar and wind energy in India. I have already told you the extent of solar and wind energy potential in India. Let me get into a little bit of fundamentals, and the first thing that you need to understand is solar photovoltaics. Solar thermal is another option. The solar photovoltaic basically are solar cells which you expose to the solar light and sun, and then it produces current and voltages. That is solar photovoltaic, we will talk about it. There is another option that use solar heat in the solar to heat something and then convert into electricity. That is called solar thermal. Solar thermal is just too expensive, and I do not know whether ever it will come up to be a great potential. Solar photovoltaic on the other hand has become the lowest cost energy source in the whole world. Wherever there is sun, the solar photovoltaic will help. The history of photovoltaic land dates back to 1839, when Alexander Edmund invented photovoltaic effect, where electrodes dipped in a conductive solution exposed to light. With light incident, a potential was developed at the electrodes, still no energy, but potential. In 1846, Willoughby Smith discovered photoconductive properties of selenium, which led to photoelectric cells, because that selenium through which you could make a photoelectric cells. Professor Abrams and his student Day introduced selenium photovoltaic cell with no moving parts. Till then moving parts were required, use selenium rod instead. And 1883, so it took quite some time from 1839 to 1883, Charles Edgar Fritz invented the first solar thin film selenium cell module. Cell made by selenium coating of copper plate and topping with a thin gold leaf layer. It produced continuous constant current with considerable force, responsive to sunlight as well as dim daylight candlelight. Fritz suggested that we may see the photovoltaic effect competing with coal fired fossil fuel plants someday. This was in 1883. Let me tell you, even in 1983 solar power was practically negligible. It was only in last 10 years that really it has gone up like anything. So, basically quantum electronics breakthrough took place in 1900, where Max Planck basically introduced that the Planck's constant and said that the photons has a certain quanta of energy h nu. Nu is the wave frequency. This basically said this much, each solar quanta solar photon will give rise to this much electricity. How much are we able to capture, etc., has to be seen. And 1905 Albert Einstein introduced light quanta called photons, following that the energy is quantized, provided an understandable explanation of photovoltaic effect and its working through semiconductive materials, good framework to all previous finding. So, when the sunlight or any other light is incident upon the cell material surface, the electrons present in the valence bond absorb energy and being excited jump to the conduction band and become free and travel. The diffusion of these electrons from one material to another material causes flow of current, thus converting light into electricity. This is the photovoltaic effect, and this is what was happening, and the photovoltaic effect became this. It was much later 1933 that Gondal-Low introduced copper cuprous oxide photovoltaic cell along with manufacturing technique. And 1941 Ohl filed the first patent on silicon solar cell. Important landmark, efficiency is 1%. Now, I talked about what is efficiency of 1%. 1% of the light falling onto this got converted to electricity, electric power. 99% remained as heat and light are good reflected and all that, only 1% did that. And this happened in 1941. 1954 Chapman D.M. Fuller reached efficiency of 6%, and now this is the first time you can start seeing, oh, now we can use it. So, adopted by Bell Labs and production of cells had started, and then the first usage of this was in space, because in space when rockets etc. go, if you want to produce electricity, this became the easiest, well, even if it was a 6% efficiency. Today 18 to 20% is more very common, 22% is fairly common, and there are experimental cells with efficiency as high up as 50%. Okay. So, that is what exists. Now, if I look at India, India is a vast, endowed with vast solar energy potential, about 5,000 trillion kilowatt hour per year energy incident on land's area, 5,000 trillion kilowatt hour. So, even if you take 20% efficiency, you are talking about 1,000 trillion kilowatt hour. The other part is distributed throughout the country, it is not concentrated, it is there in urban, rural, every area, and basically you get 4 to 7 kilowatt hours per square meter per day. That is the incident energy, 4 to 7 kilowatt hour per square meter per day. 4 when it is cloudy or not very good day like today, 7 when you have real good sun shining, and it is the most secure, anything can happen. So, sun is there, and so it is always be there. All that you need is just a photovoltaic cell panel, and you suddenly start getting energy and tapping and converting to electricity. So, even in face of all disaster, solar stays and solar power stays. As I told you, solar cell efficiency is percentage of energy incident on solar which gets converted to electric. 17% basically mean 6 square meter will convert equal to solar insolation of 1 square meter. So, if you have say 7 kilowatt hour of energy falling onto a solar panel and it is a 17% efficiency and with a 6 square meter 2 by 3 meters, then you will be able to get 7 kilowatt hour of electricity at that time. For 5 kilowatt hour energy incident per square meter, 6 square meter will produce 5 kilowatt hour. Now, this is when it is 17%. If it is a 20%, then you need smaller amount of solar cells, because 5 square meter will produce 5 kilowatt hour a day. You do not need 6 square meter. So, energy produced per kilowatt hour photovoltaic 17% would be about 1400 to 1700 watt hour per year. This is the, if I take the full year, there are cloudy days, sunny days, rainy days, very little sun. So, in most parts of India, you will see with 17% efficiency, you will see 1400 on the lower end, 1700 watt hour per year. This is 1 watt of solar. So, if you are kilowatt, you will produce 1400 kilowatt hour. What does a kilowatt? Kilowatt for 1 hour, that is a unit of electricity, that is what is going to produce. If instead of 17 you get it 20%, you can multiply 20 by 17. Remember, efficiency just means the land area used. If you have a higher efficiency, you require less area. If you have a lower efficiency, you require larger area. It does not mean that the energy goes away. Energy has heat. Sun, if it does not give heat, the whole world will die. So, I mean, solar panel has a huge sun energy is used for everything. The life comes, every tree grows due to sun energy. So, yes, we can tap part of the energy, and the part of the energy that we can tap and convert to electricity is efficiency. It does not mean that it is a bad panel. Sure, if I can get 25% efficiency, I need only 4 square meter for getting equivalent to solar insolation on 1 square meter. And we are getting close to 25%, 22% is now quite common. So, for example, if you buy a solar panel of 125 watt peak, implies that a maximum of 125 watt will be produced. This is in the best solar situation, and remember, one thing that will happen is that when it is 1000 watt per square meter, that is a kind of a considered to be it is called 1 sun, that is considered to be a very good solar insolation, and this will happen at 25 degrees standard test condition. Remember, as the temperature changes, solar panel will produce more or less amount of electricity. It basically means 125 watt hour will be produced every hour, assuming 1 sun is incident. This must also be incident at the right angle. It must be vertically incident, and we will see as it is the sunlight is coming at an angle, you will not get as much. If the temperature is high, you will not get as much. We will talk about this. Efficiency of cells does not matter except that it affects the area used. There is another interesting thing that I am going to talk about toward the end of today's lecture, that the solar power produces DC power. But we will have to of course convert it to AC if I am going to use AC power, and the whole DC versus AC debate we will talk about it. And as I told you, it also depends on the actual angle of incidence, temperature of the panel, and then the circuit which will then get this energy and either transfer it to for usage or store it. So, this circuit is called maximum power point. You want solar panel to work at maximum power point, but that is the point at which it will produce the maximum electricity. Now, you can design a poor circuit and it may not work at maximum power point, in which case a lot of energy will be wasted. So, this is a typical incidence. It gradually increases from morning, from around 6 a.m. in India, in most parts of the country, but fluctuates quite a bit, then reaches somewhere around noon or so, it reaches peak. Once in a while it may go down, it will go down. Why? Because maybe there is a cloud cover or something like that, and then it will go down and fall like this, and by around 6 in the evening you start falling. Of course, different parts of the world, timing is often adjusted as per sun timing, but I am typically giving you the number. Now, this is the important IV curve, which tells you that if I take a module, here I have taken a module, not a solar cell. We will come back to solar cell and then go to module, cell to module. So, this is a module, this is I think a 12 volt solar module, 12 volt solar module. You will see that this is the voltage at which, depending on the amount of energy falling onto this, the amount of current that flows. So, if you see if 1000 watt per meter square is falling onto it, close to 3 ampere, slightly less than 3 ampere is flowing all the way till around 12, 13 volt, and then it start dipping and then it goes down. Now, if you want maximum power, you need a multiplication of voltage and current, and that voltage and current multiplication has to peak, and you will find this is the place. At 12 volt, of course, you get up to 12 volt you get around 3 ampere. So, maximum that you can produce is around 36 watt. But as I increase the voltage becomes, let us say 17 volt here or 18 volts, the current has fallen down to 2.7, but you multiply, still you get the peak point. So, these are the peak point. Now, this is the peak point for 1000 watt per meter square, this is for 800 meter square per watt per meter square, this is 600, and the amount of light will keep on increasing, decreasing, and you must adjust the voltage such that you are at the maximum power point. This is called maximum power point, and the circuit has to be designed to operate at maximum power point. This is a circuit design, well understood, you adjust such that you are at maximum power point. This is a picture that I took from NREL. It kind of tells you different material and what is the efficiency in which year. So, if you see all the way from 1975, where solar panel cells were 1-2%, they were 6 to 8%, very expensive, these were very expensive, and then you gradually you see the efficiency going up, and most of them have gone up to 20-22%. There are cells which go higher, they will be very, very expensive, as I told you. This is a slightly dated chart, but so it gives you numbers till around 2016, 17, 18 or till around 2015. If you see there is already 46% in by 2015, but the cells which were commonly used were more like at that time 13-14%. First Solar was one company, and there were others which were being used. These were just about coming up, this green color light was just coming up, and this is the thing that was, this is the time when solar cell research was going on at University of Maine. This is the place where I did my PhD. So, some of the early breakthrough had taken place by Professor Kazmaski. I did not work with him on this, but today then it has gone up to around 17-18%, and today it has gone higher, and there are of course cells, they are expensive cells which are much higher efficiency. And today solar panels are available all kinds, it is used in rockets quite a bit, used in rural homes, it is foldable, you put it on street lights, water pumps and homes. So, all over it is used, and of course, here you see a very, very interesting thing where a concentrated solar lens is done, and then there is a solar panel, and you are using it to cook in Africa. So, this was my first chapter, and there is an assignment question, very simple assignment, you need to do this.